To continue now, we have to Professor Rui Almeida to introduce to Professor Ana Silvestre. You can start with.
Hello, present. Eu present Ana Silvestre is from Instituto Superior Técnico Universidade de Lisboa, Portugal. He do the PhD in 2002. He have in different publication 26 in Master Science, 14 citation. He work in partial differential equation, numerical analysis, and essentially mechanics, fluid mechanics, and now we present a seminar Navier-Stokes flow around moving obstacle with all pressure.
Thank you very much for the invitation and for the introduction. So today I am going to present a work which has been developed in several stages. So this is a problem in which I have started working even when I was doing my PhD. I worked for many years with Professor Giovanni Galdi from the University of Pittsburgh. One of the problems that I am going to present today was one of the first research projects in which I have worked, precisely in collaboration with Giovanni Galdi. Then I revisited this model several times, and more recently I have worked on this type of Navier-Stokes flows with Toshiaki Ishida from Nagoya University in Japan, and another collaborator, Takeo Takahashi, from Nancy, INRIA Nancy. So I am going to talk about Navier-Stokes flows around moving objects. This problem is interesting because there are several interesting questions related, for instance, with the asymptotic behavior of these flows, namely with the velocity. So I can maybe give the outline of my talk. So one of the motivations for studying exterior Navier-Stokes flows was the study, my first studies on a motion by self-propulsion of a rigid body within a Navier-Stokes liquid. And what happens in this kind of problems is that we have one rigid body and we have a liquid around this rigid body, and we can assume that the whole space around the rigid body is filled by the Navier-Stokes fluid. So this is a problem that is formulated in an exterior domain. And in these cases, we also have to prescribe the asymptotic behavior of the solutions when x goes to infinity. So what happens is that if, for instance, we observe that the fluid, we have a certain obstacle that is moving, and suppose that we observe that the fluid is at rest very far away from the rigid body. Then if the relevant variables for the flow are the velocity and the pressure, what is natural to say is that the velocity is going to zero and the pressure is going to zero when the modulus of x goes to infinity. Then, in some problems, this is not enough, for instance, to characterize in which LP spaces the velocity and pressure are going to be. Because in order to give a more precise information about whether the velocity belongs to certain LP space, we need more information about the rate of decay of the velocity and pressure when x goes to infinity. So On the other hand, the Navier-Stokes equations are a nonlinear problem, and what is known even for the classic case is that it is enough, for instance, to study what is called the Ozine problem, okay, which is a very special linearization of the Navier-Stokes equations. So, how does the Ozine linearization appears? The classical problem for the linear Ozine equations is a problem in which we have an obstacle which is just translating in the fluid. What is done is we consider a reference frame which is attached to this rigid body, and we describe the fluid flow from this reference frame. What is going to happen is that in order to have a domain for the fluid which is independent of time, we make this change of variables that puts the reference frame attached to the rigid body. When this change of variables is performed, this is going to add extra terms in the Navier-Stokes equations, okay? And this is what then gives rise to the Ozine linearization. In our case, we are going to have a more general motion of the rigid body. So we are also going to allow the rigid body not only to translate, but also to rotate. And this motion of rotation, when we see the equations of the fluid described from the reference frame which is attached to the rigid body, this change of variables is going to cause even more extra terms in the Navier-Stokes equations. So not only we will have terms that are due to the motion of translation of the rigid body, but now we will also have some terms that are due to the rotation effect of this rigid body. And this is what we are going to call the generalized Ozine problem. So the generalized Ozine problem is an exterior problem which arises from the Navier-Stokes equations when they are described from a reference frame which is attached to a rigid body which is translating and rotating. In order to understand the rate of decay of the velocity and pressure when x is very far away from the rigid body, so when x goes to infinity, when the magnitude of the space variable goes to infinity, we should understand very well the behavior of the generalized Ozine problem, and this can be done with the help of the generalized Ozine fundamental solution. So, in order to understand Navier-Stokes exterior flows, and in particular to understand the effect of the motion by self-propulsion of a rigid body in a Navier-Stokes liquid, it is very important to understand the properties of the generalized Ozine fundamental solution, which include effect of translation and rotation of the obstacle. Now, the self-propelled motion that I am going to introduce as a motivation is an interesting motion, not only from the physical point of view, but also from the mathematical point of view. Because when we are dealing with exterior flows, and this is not the case only with fluid flows, even if we have the very simple Poisson or Laplace equation in an exterior domain, we know that we don't have anymore, in general, the L2 norm of the solution finite, okay? So, in some exterior domain, when we are studying some exterior flow, we cannot expect that the velocity is going to have finite kinetic energy. So, in other words, we cannot expect that the velocity is in the space L2. Because we are in an exterior domain, this property is lost, and somehow this is related also with the loss of the Poincaré inequality. So when we study, for instance, a Navier-Stokes flow in a bounded domain, what we get in terms of energy estimates is an estimate for the gradient of the velocity. When we are in some bounded domain, which allow us to conclude that the velocity is in L2, so that the flow as finite kinetic energy is the Poincaré inequality. But that is possible when we are in some bounded domain. In an exterior domain, we cannot use it anymore. And so, in general, for a very general Navier-Stokes exterior flow, we don't have the velocity in L2. But that happens if we have a self-propelled motion. So self-propelled motions are interesting, not only because of the applications, but also because of the mathematical properties. Now, the importance of understanding very well the asymptotic behavior of the velocity and pressure when we are in an exterior domain. It's also important, for instance, to understand if the solution is unique, okay? Because to study uniqueness, we need to subtract two eventual solutions. We need to get a kind of energy equation for the difference of these two eventual solutions. And to get this energy equation, okay, even the energy equation for the flow, we need to do integration by parts in an exterior domain. And to do this very rigorously, we need to know what is the rate of decay of the velocity when the magnitude of x goes to infinity. So there are several problems here, mathematical problems, and also problems with physical interest. The energy equation is also interesting from the physical point of view, and all these physical and mathematical problems require the knowledge of a precise asymptotic behavior of solutions when we are in the exterior domain. Another interesting application in which I have worked in recent years is the optimal control for an obstacle moving in a Navier-Stokes fluid, in the sense that, for instance, we want to optimize the efficiency of motion of this obstacle, okay? This can be also formulated in terms of saying that we want to reduce the work that this rigid body has to do in order to overcome the drag that is exerted by the fluid on the rigid body. And so when we are studying this optimal boundary control for drag reduction, we also need to do a kind of transformation of the cost functional with which we are going to work. And in order to, for instance, to establish the well-posedness of the state equations, it is also important to understand the asymptotic behavior of the solutions of the state equations, and also the behavior of other problems which characterize the optimal controls. For instance, when we want to give a characterization of optimal controls, we have to understand the well-posedness, and in the case of problems defined in the exterior domains, also the asymptotic behavior of the solutions of certain linearized problems, and another problem which is called the adjoint problem, okay? So in this description that I have given here, I have mentioned several problems related with Navier-Stokes equations in the exterior of some obstacle. which have to be very well understood in terms, for instance, of the asymptotic behavior of the velocity and pressure, okay? So this is going to be a very important part of my talk. And in particular, I am going to give some importance to this generalized Ozine fundamental solution, which is going to give us somehow the information about the asymptotic behavior that we want to understand. Okay, I will start with a formulation of the problem. So I have talked here about motion by self-propulsion. I am going to give some applications and give the formulation of this problem. So there are several examples in nature in which we can say that we have motion by self-propulsion. For instance, when we have a submarine moving in the sea, we can say that the submarine moves by self-propulsion. Also, some very small microorganisms that move because they are able to somehow perform some motion of very small cilia that they have in their surface, and this is what makes them move. So these are cases in which, for instance, in the case of these microorganisms, gravity here is not so important. What is important for their motion is this, let's say, this distribution of velocities that they are going to generate on their surface, okay? So when we say that a certain rigid body performs a self-propelled motion when it moves inside a certain fluid F, is when the total external force acting on the fluid is zero, okay? So there are no forces acting on the fluid, and in order for the motion of the rigid body to be by self-propulsion, we also have to guarantee that the total force, the total net force and torque external to the rigid body and to the fluid, which are acting, are identically zero. So in this case of these very small microorganisms, actually they are not exactly rigid bodies, but they are so small that we can consider them rigid bodies. Also, when we have these very small microorganisms, since their motion is very slow, sometimes we can also just use a linearization of the problem, okay? And instead of working with the nonlinear Navier-Stokes equations, we can just work, for instance, with the Stokes equations or some other linearization of the Navier-Stokes equations that can take into account, for instance, the motion of the microorganism. Okay. So first, I will give an idea of the equations of motion in some inertial frames. So here we are seated in a frame, okay? The frame is fixed, and we are watching the motion of the rigid body, and we are also watching the motion of the fluid around this rigid body. So what happens in this inertial frame is that the fluid domain is going to change with time, okay? And this is something that also makes the problem difficult. This is a characteristic of fluid structure interaction. So the domain depends on time, and the domain also depends, for instance, on the motion of the rigid body. These are the equations of motion for the liquid, okay, around the rigid body. So omega of t is the fluid flow around the rigid body. The first equation here is the conservation of linear momentum. So this is typically the Navier-Stokes equation. This is a nonlinear term, is a convective term. And here we have the divergence of a tensor, which depends on the velocity and the pressure. Okay, this tensor is 2 times the symmetric part of the gradient of u, and then here we have the pressure, which is a scalar, multiplying by the identity tensor. So in these equations, the velocity is a vector quantity and the pressure is a scalar, okay? When we take the divergence of this tensor, what we get is the viscosity, which is this constant here, times the Laplacian of the velocity. So this is a vector quantity, okay? If we are in R3, this will have 3 components. And then the pressure is a scalar, but the gradient is going to have 3 components if we are in R3. So this is the Navier-Stokes equation. This is the equation that tells us that the fluid is incompressible, okay? We are dealing with a liquid, so the divergence of the velocity is equal to 0. We want that the velocity goes to 0 very far away from the rigid body. So this is the condition that I was talking before. This is something that we impose already in the equations, but then we want to know this limit with more details. We want to know the rate of decay when we write this limit when the modulus of x goes to infinity. In the time-dependent case, we put here some initial condition for the velocity, just for the velocity, not for the pressure. And now, finally, we have here some boundary condition on the boundary of the rigid body. So what is this? This is the velocity of the rigid body, which is of this form. So a rigid body velocity is always characterized by a translation and a rotation, okay? Here, we also consider the possibility, as in the case, for instance, of these microorganisms, that there is some motion on the surface of the rigid body. On the submarine, we can, for instance, assume that there is also something moving here, which is in fact what makes the submarine move. But in fact, the size and shape of the submarine is not going to change during the motion. So we can consider it still a rigid body. And so the boundary condition for the fluid on the boundary that also belongs to the rigid body is something that has to do with the motion of the rigid body and something that has to do with the motion of the surface of the rigid body. Okay, so if we know the velocity of the rigid body and this velocity on its surface, then we can just solve this system of equations for U and Q, provided that we also know the evolution of this fluid domain, okay? But there is another problem that I also would like to describe, which is the problem in which the motion of the rigid body is also unknown. And in this case, we have to add some equations to describe the evolution of the translational velocity of the rigid body and also the rotation of its center of mass. And these are these 2 equations where we also see the this first term here, this integral, where we see the velocity and pressure of the fluid is the action, let's say, of the fluid on the boundary of the rigid body. This is the normal, okay? And here we have some term that has to do with the presence of this velocity on the surface of the rigid body. And here we have the corresponding equation now for the angular velocity, okay? So here, what we have is a kind of a coupling between the equations of motion of the fluid and the variables for the motion of the rigid body. So also, if we already know the velocity and pressure of the fluid, we can find the motion of the rigid body just by solving this system of equations. In general, both of them are unknown, the motion of the fluid and the motion of the rigid body, okay? And so we have to consider the two equations coupled. Now, what we have here now is the equations of motion. This is just for the fluid. After we make the change of variables and we consider a reference frame that is attached and also rotates with the rigid body. So what is the advantage of making this change of variables is that the fluid domain now is fixed, completely independent of time. It will be known if we consider it as some reference frame that we prescribe in the inertial frame. But we have to pay a price for having this advantage of working in a fixed domain, which is some extra terms in the Navier-Stokes equations. So these were the previous terms in the Navier-Stokes equations, okay? And now we have here some terms that depend on the velocity of the rigid body, which in the frame that is attached to the rigid body now can be written in this form here, okay? So, since we are in an exterior domain, the fact that we have here a new term where we also have x, okay, and this x now belongs to the domain omega, which is an exterior domain. So we have here a term which becomes unbounded when modulus of x goes to infinity. And this is a problem when we are studying this exterior Navier-Stokes problem, okay? And in particular, if we want to know the precise behavior of this limit here, okay? So the classical Ozine problem that I have already mentioned is the problem in which, after this change of variables, which considers a reference frame that is attached to the rigid body. So the classical Ozine problem is the problem in which we will only have here a term related with the effect of translation. Now, we also want to account for a possible rotation of the rigid body, okay? And that effect is going to appear in this term because we will see here the complete velocity of the rigid body, but by the change of variables, we also see another term there related with the angular velocity of the rigid body, okay? So these are the Navier-Stokes equations in the exterior of a translating and rotating rigid body. In a problem that I am used to work, we also assume that the motion of the rigid body is unknown, and so we also have to solve for the translational velocity of the rigid body and angular velocity. And in the frame that is attached to the rigid body, the equations take this form. Okay, so they become a little bit more complicated when the motion is described in this reference frame, which is attached to the rigid body and also rotates. Okay, so let's see. This is the complete system if we want to study the fluid structure interaction problem, where the velocity of the obstacle is also unknown. If this motion is known, then we just have to worry about the exterior Navier-Stokes equations, which is this system here. Okay. Now what I have here, so in the previous problem, this was still the time-dependent problem, okay? Now we can consider the steady problem associated with this one, and the steady problem is the problem in which which assume that the variables will not depend on time, so we just neglect this time derivative here, the same here and here, okay? So we get this system. So this first part here is just the steady Navier-Stokes equations in the exterior of a translating and rotating obstacle, okay? This is the set of equations that we have to have if the motion of the rigid body is also unknown. And here we are, again, I am going to say, we are describing the motion from a reference frame attached to the body. Okay, so this is now some specific description of self-propulsion. So self-propulsion can be produced by means of drawing fluid inwards across portions of the boundary of the rigid body and expelling it from other parts of the boundary, okay? And this means that the net flux of momentum across the boundary is going to be non-zero, okay? So in this case, where we allow for this type of self-propulsion, let's say, this integral here has to be considered in the equations, okay? So we have to work with this integral, which is a little bit more complicated, but in some cases we can consider that the motion is caused just by moving tangentially portions of the boundary, and this happens when there is a motion by belts. In this case, the previous equation can be a little bit simplified, because if we are considering tangential motions, then we can assume that the distribution of velocities on the surface of the rigid bodies of the rigid body is only tangential, so the normal component is zero. This term also simplifies, and somehow we can drop these complicated integrals here, and the problem simplifies a little bit in this case. So when this V star is tangential, the problem becomes a little bit simpler in the case that we don't need to consider these two integrals, and this is also a type of motion that we observe in nature. Okay, so I am going to recall the notation. So V, capital V, is going to stand for the velocity. Now I am going to consider steady motions, and in this steady motion, the translation and rotation of the rigid body are just constant. They do not depend on time anymore. This is described in the reference frame attached to the rigid body. And I am also recalling the expression of this tensor, okay? So if we want to talk about a direct problem, since after I am going to describe a control problem, we can say that in this case, this V star is given, okay? And in the case where the capital V is also given, we just have to solve for the Navier-Stokes equation. So when capital V and V star is given, we solve for the first four equations. And this is already difficult because, again, we have here some term that becomes unbounded when x goes to infinity. If we also want to put the motion of the obstacle as one unknown, then we have to add to our system the equations of motion for the rigid body, which are these equations here. And in this case, capital V is going to be unknown, so chi and omega are going to be unknown. Okay, so these are some references in which I am going to base my talk. This problem of motion by self-propulsion, I think that it was for the first time given in a very formal mathematical way, so more systematically in terms of its mathematical description in a paper by Galdi. Then I worked also in motion by self-propulsion, for instance, in the attainability of steady states. concerning the asymptotic behavior of the Navier-Stokes equation. So in understanding with detail what is the rate of decay that is behind this limit here. I have also some work with Giovanni Galdi concerning just the case in which the motion of the obstacle is given. In particular, we tried to understand if the formation of a wake region is still present when we have an obstacle that is also rotating, because what we observe in nature when we see a rigid body translating in a fluid, we see a kind of wake region behind the rigid body. So we observe that there is a different behavior of the flow inside this wake region that is described by the motion of the rigid body and outside this wake region. And we would like to have, in terms of the motion of the rigid body, a way of describing this wake region. Okay, very recently I have worked on the control problem for motion by self-propulsion with Takeo Takahashi and Toshiaki Ishida. And here, since we had to work again in the exterior domain, since we needed, for instance, the energy equation for the flow, we needed to do several integrations by parts to obtain, for instance, a linear system that allow us to solve our control problems. All of these auxiliary problems needed the precise asymptotic behavior of the velocity when the modulus of x goes to infinity. So even though here we are interested in the control problems, we still have to do a lot of work to understand very precisely the asymptotic behavior of the velocity. The asymptotic behavior of the pressure is not a big problem here, because basically we will see that the behavior of the pressure is not so affected by the type of motion of the rigid body. So it will be basically the same if there is rotation or if there is translation. So the velocity, the pressure is not the problem. The velocity is going to be affected by the type of motion of the obstacle. Okay. Then, of course, I should include here in this list of references many other authors that have worked in the exterior generalized Navier-Stokes equations, which include Reinhard Farwig, Mads Kidd, Paul Doring, Sharka Nekazova, and her collaborators in Czech Republic, like Krakmar, Patrick Penel, and many other authors that have produced hundreds of papers about the exterior Navier-Stokes equations. And in the last decades, many people have been interested in these generalized 3D Navier-Stokes equations, which are the equations in which we have these extra terms that are generated by not only the translation, but also by the rotation of the rigid body. Okay, so now I am going to focus on the generalized Ozine problem. So this is just a linearization of the Navier-Stokes equations, which will allow us to understand the asymptotic behavior. And I am going to start to show by this picture, where this is, in fact, I am talking basically about the 3D case. This is the 2D case that is easier to observe, okay? But what we see here in the 2D case, we also see when some obstacle is moving inside the ocean, the ocean or the sea, or in the within a river, for instance. So when we see, for instance, a duck in a lake, we see the formation of this region here, which is the wake region, okay, which appears as the duck is moving, okay. It is formed behind the duck, and we see that there is a difference between the characteristics of the flow inside this wake region and outside. What we would like to do is to see this different behavior expressed by the equations, okay, by some form, by some information that comes, for instance, from the velocity field, okay? So let's consider the linearized Navier-Stokes equations, and this linearization that I am considering here is just the classical Ozine linearization. In the classical Ozine linearization, we only have translation, okay? So for the moment, rotation is not there because I am just going to recall what is the rotation, the effect of translation in the fluid flow. So these are the Ozine equations. Again, the divergence of V is equal to 0 because of incompressibility. This is the domain omega is an exterior domain, so is the exterior of some obstacle. So if this is our obstacle, the domain omega is everything around this duck, and we can have we have to put boundary conditions on the boundary of our obstacle. We have V star that we have already used before, and we are going to say that very far away from the rigid body, the fluid is going to be at rest. So we put here the limit of V of x equals to 0 when modulus of x goes to infinity, okay? We put here some forcing term F, and later on, when we try to analyze this problem, for instance, prescribing some asymptotic behavior for this force F, we should take into account that we are going to take this F in the form of divergence of this tensor product, because this is what is going to give us the nonlinear term of the Navier-Stokes equations. So we put here this F, because then we are going to apply a kind of fixed point argument in which this will be fixed in certain iteration, okay? And then we apply a fixed point theorem to find the velocity, okay? So let's see what happens. This is a classical case which is very well known. So in this case, we know that the asymptotic behavior is described by a function in which we have modulus of x, and here we have some term that depends on the translational velocity of the obstacle, okay? So this key here is the same vector that appears here, and this is related with the translation of the obstacle, okay? Even though I have the picture in 2D, I will consider the 3D case, okay? In fact, the 2D and the 3D case can have different properties. This is something very interesting in the Navier-Stokes equations. So this is going to give us the precise description of the asymptotic behavior of those in equations. So we have here the modulus of x, and we have here something that we are going to call S of x. And this is in fact what is going to describe the wake region that we observe here, okay? We should think about the corresponding region in a 3D flow. So what we can say is that not only V is going to, the limit of V of x is going to be 0, but it is going to decay like 1 over this function. So if key is different from 0, it will decay a little bit faster than just modulus of x, okay? And the wake region can be described in terms of this function here, S, which depends on the translation of the rigid body. So the wake region can be described by S of x less or equal than 1. We can see from here that the rate of decay inside the wake and outside the wake is different. Okay, so outside the wake it will decay faster. Now we want to understand what happens when not only we have translation of our rigid body, but we also have rotation. We want to see what is the effect of rotation in the flow. And of course that if the rigid body is translating, we still expect, for instance, to see the formation of the wake. But we may also expect that the effect of rotation is going to do something on the wake, okay? We also expect the disturbance somehow of the wake by the rotation, okay? So let's see. I will not show the calculations that lead to the results that I am going to show because they are quite heavy, but we can show that, okay, so first I am going to, I can show what is going to happen. So instead of the previous function that gives the rate of decay of the velocity, where before we just had this key here, now we also will have the effect of rotation, okay, in a somehow strange way, because there is some interplay with the translation and the rotation, okay? So let's see how this appears. So let me go back. So when we want to understand the asymptotic behavior of some linear equation, what we usually do is to understand the fundamental solution. So somehow we can say that the fundamental solution is the solution in the case when we are in the whole space, and this f here is just the Dirac delta concentrated on the origin, for instance. Okay, here we have to move it because since this term also depends on x. If we want to obtain the fundamental solutions here, we should put something like delta of x minus y, for instance. Okay, so let's try to construct the fundamental solution. It has to incorporate the effect of translation and rotation. Okay, so what we have here is, let's assume that the velocity is given by some vector zeta, and the rotation is omega. This matrix here is the matrix that expresses some, so if we want to write omega cross x, then we can just apply this matrix to the vector x, okay? We should also consider the exponential of this matrix here, which expresses the rotation. And now we consider this unit vector and some vector that is going to allow us to do some translation that will be good for obtaining the fundamental solution. And after some calculations, we get an expression which is a little bit complicated for the fundamental solution. So what is going to happen here is the following in terms of the Ozine fundamental solution. What we get for the pressure, so the fundamental solution is going to be composed of a part related with velocity, another part related with pressure. What we see is that the part related with pressure is not affected by the translation of the rigid body and by rotation, but the part for the velocity is affected by translation, as already happened for the Ozine case, but now it will be affected in a more complicated way by rotation. So in fact, we are going to obtain the fundamental solution written in terms of some integral. This is a kind of integral in time, okay, where we see here inside this capital V is the fundamental solution of the time-dependent Ozine problem, where instead of translation, we have translation projected in the direction of rotation. And then here we have some other terms that come from the rotation. So the effect of rotation makes, for instance, the fundamental solution very complicated, okay? But then we can take advantage of the knowledge of this fundamental solution for the Ozine problem. And in fact, okay, after doing some decompositions, for instance, of the translation and of the velocity of the rigid body itself. So what is important here is to do some decomposition that takes a projection in the direction of rotation, and then something that is orthogonal to the direction of rotation. And we can express the fundamental solution that takes into account the translation and the rotation. We can decompose it, we can decompose it into three main parts. And the most important part is this one. So this is again, this is a projection matrix, and this is a kind of projection again in the direction of rotation. Okay, so what we have here, this is going to be the dominant term for the asymptotic behavior, and what we have here is what is going to strongly contribute for the asymptotic behavior of the velocity is a projection in the direction of the rotation, okay? And then is a kind of Ozine fundamental solution coming from here, where the translational velocity is also projected in the direction of rotation. And then we have some other terms which are not so important for the leading term in the asymptotic behavior that are associated with rotation, okay? So the form of the fundamental solution is very complicated. To perform an analysis that allow us to conclude that this term with one here is the main term in the asymptotic behavior is not completely trivial, okay? So there are a lot of very precise calculations that have to be done. And after this, we arrive to the conclusion then that the velocity of the generalized Ozine problem decays to zero in accordance with these estimates. So it will decay to zero like 1 over a function which is described by this expression. And again, what we see here is that what is important is the projection of the translational velocity on the direction of rotation. So, because of this, concerning the formation of the wake, we see that if the translation and the rotation are orthogonal, then these terms disappear and we just get a kind of Stokes solution. So in this case, we don't see the formation of the wake. There is no wake. So when K and omega are orthogonal, what happens is in this case is that the effect of rotation destroys the wake. If there is rotation and the rotation and translation are not orthogonal, then we see a formation of the wake, and the width of this wake will depend on the angle between the translational velocity and the angular velocity. Okay, with this behavior of the velocity, now we are able to solve, for instance, an exterior generalized Ozine problem. If we assume that the forcing term that we have there has a certain decay, okay, then we are able to show that the velocity is going, that there is a unique velocity and pressure, and that the pressure is going to have this decay. And we also have estimates for the gradient of the velocity, for the pressure and for its gradient. In particular, we can show that the pressure is in L2, okay? And from here, we can get some other LP estimates for the velocity. But in particular, this asymptotic behavior is going to be very important for us. Then we can combine these with a fixed point argument and to get the existence and uniqueness of solutions for the Navier-Stokes equations, assuming that the data are small. So assuming, for instance, that the velocity of the rigid body is sufficiently small, okay? So this is what allows us to understand the complete behavior of the velocity. Now, what we have here is a term which is very interesting because it's a term that appears in the first self-propelling condition. And if you remember, I said before that in general, when we are in some exterior domain, we cannot expect that the velocity is in L2. But if this quantity here is 0, then we can prove that in fact the velocity is in L2, okay? And this term that we have here is precisely one term that appears in the formulation of motion by self-propulsion, okay? So the term that I denoted by N is a term associated with this extra condition for motion by self-propulsion. So what we also have is, if we have motion by self-propulsion, in particular, if this equation is satisfied, then the velocity of this system is in L2. And this is not usually what happens in exterior domains. Okay. Now, I have also here some estimate for the L2 norm of the velocity when it is finite, but I am not going to give much details. Now, about the control problem. What we want is to reduce the work needed to overcome the drag. And this can be formulated in terms, a cost functional that can be described by this way. This is the velocity and pressure of the fluid. And now, we also want to reach a certain target velocity, okay? Now, we would like to transform this expression in order to get a cost functional, for instance, of quadratic type. That will be very useful to apply, let's say, some control techniques. In order to this expression, okay, let's consider that these are our state equations. In order to simplify the cost functional, we need to know the asymptotic behavior of the velocity, because if we know what is the asymptotic behavior of the state of the velocity and pressure of our state equations, then we can show by means of the energy equation that the term that we want to minimize can be written in terms of the L2 norm of the symmetric part of the gradient plus this extra term here, okay? And for instance, in the case that we are looking for tangential velocities, this term will disappear, okay? So the asymptotic behavior of the Navier-Stokes equations is important, for instance, to obtain the energy equation, because to pass from here to here, we have to do integration by parts, and we have to know the asymptotic behavior of solutions. In order to prove that solutions are unique, the asymptotic behavior is also important. So once we have this formulation of the cost functional, then we can use, it's very technical what we have to do in this problem, but we are able to show that we can minimize this quantity, provided that the controls are also small, and we can show the existence of optimal controls for our problem, okay? Then we can also consider a Lagrangian, an augmented Lagrangian associated with our problem, and we can obtain the adjoint problem, which is important to characterize the optimal control. And here we see the same kind of problem that we had already found with the terms that come from the translation of the rigid body. So to show the well-posedness of this problem, we can also use what we have already obtained for the generalized Ozine problem, for instance. And we can give this characterization for the controls, okay? In the case of the tangential controls, it is simpler. So in terms of the solution of the adjoint problem, we can give this characterization, okay, for our control problem if our optimal control is this velocity v star hat, okay? So this is the solution of, this is the pressure, this is the corresponding optimal state, and this V hat and Q hat are solutions of the adjoint system, which can also be analyzed using our previous study of the generalized Ozine problem. And I will finish here. Thank you very much.
Thank you very much. It's a very interesting and nice presentation. We have some questions, please. Comments. I have no question. It's very interesting, and thank you for your presentation, and nice to meet you.
Thank you very much for the invitation. It was a pleasure.
Professor Juan, next meeting.
Tengo cuestión o profesor Lionel Rosier.
Yeah.
Can I ask a question?
Yes, please.
Yes, please, Anna. So you prove the existence of some optimal control. So can you prove that your optimal control is bounded when the viscosity coefficient tends to 0? Is it true or not? Ah,
okay. I don't know what to answer you. We didn't think about that. So when because I think that even before thinking about the optimal control problem, we should also understand what happens with the state equations, right? And even that we didn't think about it. I don't know what to tell you. It's a very interesting question, but I don't know.
Okay, so it's work to be done.
Yeah, it's a good. It can be a very nice project to proceed with our study. Thank you very much.
Okay, thank you very much. Thank you.
Thank you, Ruiz. Thank you a lot, Professora Ana Silvestre, for your amazing talk.